Thank you very much, Konrad. And I would like to welcome Carmen Rodrigo. Hi. Nice to meet you. As far as I know, you represent the University of Zaragoza? Yes? Okay. So I think that we start half an hour for the presentation and then 10 minutes for discussion.
Thank you very much. Okay, first of all, thanks very much for the nice introduction. And also, I would like to thank to the organizers for inviting me and giving me the opportunity to present my work here. And also, of course, I am very honored to be the first one to open the scientific program, so thank you very much. So today, I'm talking about the efficient solution of mixed-dimensional models in fractured porous media by using monolithic multigrid methods. This is a joint work with my colleague, Francisco Gaspar, also from the University of Zaragoza, and Andrés Arrarás and Laura Portero from the Public University of Navarre, also in Spain. So the outline of my talk will be as follows. So I will start by motivating the problems that we consider here. Then I will talk a bit about the different models that people use in this framework. I will focus on the mixed dimensional models, and in particular, I will start with the Darcy-Darcy coupling. And then I will briefly introduce the discretization that we use, and I will focus in our main contribution, that is the design of an efficient solver for the discretization of this problem. Then I will present some numerical experiments in order to show the robustness of the proposed method. And in the second part of the talk, I will talk a bit about the extension of the proposed approach to the nonlinear Darcy-Forchheimer model, and I will present also some more numerical experiments with some conclusions. So our main focus here is the solution of, to study the fluid flow in a porous media in the way that we have a fracture network included in this porous media, such that the fractures can be preferential flow paths for the fluid, or also can be barriers for the fluid flow. These problems are very important, and in the recent years they have received a lot of attention due to the essential role that the fractures play in many applications, many real problems, such as, for example, petroleum engineering, also the storage of CO2 and nuclear waste, the production of geothermal energy, but not only in applications for related to hydrological processes, but also, for example, in biomedicine, where the circulatory system provides relevant models for preferential flow in order to simulate the blood circulation in the capillary network. As a consequence, for the numerical simulation of these problems, it's very important to develop efficient solvers and appropriate discretizations for these problems. In the last years, most of the focus has been paid in the development of discretizations, but in this talk, my focus will be in the design of a monolithic solver for this problem. So depending on the scale under consideration, fractures can be incorporated to flow models in two different ways. If we think about the small scales, where the specific location of the microfractures are difficult to determine, then usually the so-called dual or multiporosity models are considered. The basic idea of these models is that you consider that your flow domain consists of mainly two dominant pore networks, the microfractures and the macrofractures that will correspond with the fractures. And then there is a mass transfer between these two main pore networks. On the other hand, at large scales, if you know a priori the location of the fracture network, then the mixed dimensional models are usually considered. And these discrete fracture models are the ones that we are going to consider here. However, these discrete fracture models usually require the use of very fine grids in the fracture domain in order to obtain accurate approximations. This fact, together with the fact that the aperture of the fracture is very small compared with the length and also compared with the whole porous domain, this implies that the computationally expensive discretizations are needed. In order to avoid this, the idea is to use a reduced model in which the fractures are treated as n-1 dimensional interfaces inside of an n-dimensional porous media. Due to this, these models are also called mixed dimensional models. And then in this framework, the flow can be modeled by different models in the fractures and in the porous media. Here in this talk, in particular, I will consider the Darcy-Darcy coupling and the nonlinear Darcy-Forchheimer coupling. So for simplicity in the presentation, I will start with by considering a single fracture. So the setting of the problem is the following. So we have a porous media omega, where a subdomain omega f here represents a single fracture that splits the porous media into subdomains. Then we would have the corresponding equations, for example, Darcy's law in every of the subdomains. And then we have, of course, appropriate coupling conditions that preserve here the continuity of the pressure and the normal flux between the subdomains. So this would be the so-called equidimensional or transmission problem. And then the idea is based on reduction model techniques. What we do is to collapse this omega f, the fracture domain, into the line gamma in the way that we integrate along the thickness of the fracture, and then we can obtain the so-called interface problem or mixed dimensional model. I'm not going into the details here, but all the details in the derivation are in this, can be found in this paper here. So in particular here, I will consider first the Darcy-Darcy coupling. So this means that we have Darcy flow in the porous matrix and also Darcy flow in the fracture. This equation here would represent the tangential component of the Darcy flow in along the tangential direction in the fracture. And this second equation here would represent the mass conservation within the fracture, in the way that this term in parentheses represents the contribution of the subdomain flow to the fracture flow. Here, I didn't say Kf tau is the tangential component of the permeability tensor in the fracture. And then, of course, we need to obtain the interface condition that is obtained by averaging Darcy's law in the normal direction to the fracture. And then here we have also that we use a quadrature rule with the weights xi and 1 minus xi, and here Kfn is the normal component of the permeability tensor in the fracture, and xi is a parameter that is related with the pressure cross profile in the fracture. So this is the problem that we have. In order to do the discretization, so we first consider the weak formulation of the problem. So in order to do this, we introduce appropriate function spaces for the pressure and for the velocities, and of course the corresponding bilinear and linear forms, giving rise to the standard mixed form of the variational problem, as we can see here. The uniqueness and existence of the solution of this problem has been already studied and can be found in this reference here. So in order to apply our finite element discretization, we consider a rectangular partition of the porous media subdomains in the way that these meshes match in the interface and then give rise to a unique partition of the gamma, of the fracture. Then we would obtain a global mesh, which in 2D, for example, would contain two-dimensional elements in the porous matrix and one-dimensional elements in the fractures. In this way, by considering the lowest order Rabiar-Thomas mixed finite element methods in the subdomains, we would obtain the corresponding discretization, and we can define the global function spaces of finite elements. In this way, what we do is we follow this work by Russell and Wheeler, and then we consider some numerical quadrature rules in order to evaluate some of the integrals that appear in the derivation of the discretization. And in particular, we consider this bilinear form here. And as a standard, we would obtain the mixed finite element formulation of interface problem, that is the one that we have here. At the end, when we use these quadrature rules, the discretization that we obtain by this mixed finite element method is equivalent to a cell center finite volume discretization, as is explained here in this paper. And then, as a standard also, we can write our discrete problem as a large linear system of algebraic equations. Then our main focus here is the efficient solution of this large system of equations. And in particular, since for this type of systems, multigrid methods usually show a great performance, our choice for the solver will be a geometric multigrid method. So multigrid methods usually combine two principles. First one is the smoothing property of the classical iterative methods that efficiently eliminate the high components of the high frequency components of the error. And then in this way we obtain an error that is not small but is smooth. This error can be well represented on a coarse grid in which the low frequency components of the error become high frequency components, and then the classical iterative method again can act efficiently on these components. In this way, the geometric multigrid method will use a hierarchy of grids in order to eliminate all the different components of the error. And of course, the behavior of this method strongly depends on the choice of the components, and then it's very important to appropriately choose every component in the method. So we will first have to define the hierarchy of grids that we consider, and we will have to see how to discretize our problem in every grid in the hierarchy. Then I will need some way in order to transfer the information for one grid to another, from fine grids to coarse grid and vice versa. Also, how to visit the coarse grids, the type of cycle of the multigrid method. And then one of the main components, that is the smoother, so the classical iterative method that we will apply in order to do this smoothing procedure. And of course, the number of times that we will apply this method. So once that we have the components of our method, this would be the two-grid algorithm. So we first do some pre-smoothing. So we apply the classical iterative method on the fine grid. Then we compute the residual, and then we restrict the residual to the coarse grid, where we have to solve the residual equation. Then we will interpolate this correction, and we will correct the current approximation on the fine grid, and then we can apply again some post-smoothing steps. If instead of solving exactly the residual equation on the coarse grid, we apply recursively this same algorithm, what we obtain is the linear multigrid method, that is the one that we will consider here. And now I'm gonna present the components that we choose in order to deal with this mixed dimensional problem in fractured porous media. So first we need the hierarchy of grids, and then the idea is to consider first a coarse grid that takes into account the location of the fractures in the system. How we take into account the fractures? We will consider the coarsest grid that has the fractures as an edge of the elements of the mesh. So this means the following. If we have this example, here the solid lines represent the fracture network, and then we need to obtain the coarsest mesh in which all these fractures are edges of the element of an element of the mesh. So then we construct the grid as these dashed lines that we can here, and then we can see here. And you can see that for each fracture we have that this is contained on the subset of edges of the mesh. Once that we have this coarse mesh, the idea is to apply a regular refinement process to this coarse mesh in order to obtain the target grid in which we can solve our problem. And this is done by a standard regular refinement. So every cell here is divided into 4 equally sized cells. And here in this picture, we can see the location of the unknowns for the porous matrix. So we have pressure in the midpoints of the cells, and then the velocities on the edges. And for the fracture, we have the pressure in the middle and the velocities on the edges of the edge. And this would be the location of the unknowns in the refined mesh. Once that we have the hierarchy of grids constructed in this way, in our case, we are going to discretize directly our problem in every mesh in the hierarchy. And also, the cycle that we consider is a W cycle with 2 pre and 2 post smoothing steps. This would be the setup for our multigrid method. Now we need to choose the intergrid transfer operators and the smoother. And the key in order to do this in our framework is to consider what we call mixed dimensional components for the multigrid. So the idea is that, for example, for the intergrid transfer operators, we will consider 2-dimensional restriction operators in the porous matrix, but 1-dimensional intergrid transfer operators on the fractures. And then we will combine these components in order to get this mixed dimensional multigrid method. So for the restriction, we consider the standard 2-dimensional restrictions on a staggered grid for the velocities and for the pressure, and the 1-dimensional counterparts for the velocity and for the pressure. Regarding the smoother, the idea is the same. So we will consider a mixed dimensional smoother, but also here we have to take into account that our problem, our system, is of saddle point type character. So then this has to be taken into account, and then we will select our smoother from the multiplicative Schwarz iterations. In particular, we will consider the so-called Banca smoother that I will explain now. And due to the mixed dimensional character of our problem, our relaxation will be composed of 3 consecutive steps. First, we will update the components, the unknowns that are in the porous matrix. Then we will do the relaxation for the fractures, and then we will update the intersections of the fractures, 0-dimensional intersections. For the 2-dimensional smoother in the porous matrix, we consider a 5-point Banca smoother that in which the idea is to simultaneously update all the unknowns that are involved in the discrete divergence operator of the equation. This means that these 4 velocities together with the pressure point will be updated together, and then for each cell in our grid we need to solve a 5x5 system of equations. Then in the fractures we will do the same idea, so we update all the unknowns that appear in the divergence operator together. In this case, we don't have only the pressure for the fracture and the velocities for the fracture, but also we have 2 velocities of the porous matrix that correspond to the 2 elements that coincide in the fracture. So we will update these 5 unknowns together, 3 unknowns from the fractures and 2 of the porous matrix. And then finally, for the intersections, we will apply a block Gauss-Seidel by updating together all the velocities, all the fracture velocities in that intersection. So this would be our smoother. And then now I want to present some numerical experiments in order to show the robustness of this multigrid method for different settings. In the first numerical experiment, we consider an horizontal rectangular slice of porous media in which we have impermeable bottom and top, and we have a pressure, a concrete pressure described on the lateral walls, here P equal to 0, here P equal to 1. Then the permeability in the porous media is equal to 1, and we consider a single fracture that split this domain into different subdomains. First, we consider that the permeability in the fracture is constant, and later we will change this in order to see the robustness of the method. That first, we will consider a constant permeability here, and we will see how our method behaves depending on the value of this permeability. But before that, we show here in this picture two figures of the pressure distribution of the solution when a big permeability and a small permeability are considered in the fracture. So the first one is for a big permeability, so this means that the fracture is highly conductive, whereas in the second case we have a small permeability, so we have a blocking fracture that can be seen clearly here in the distribution of the pressure. Now, in order to see the behavior of the multigrid method for different values of the permeability in the fracture, in this table we show the number of iterations of the multigrid method that we need in order to reduce in a factor of 10 to minus 10 the residual, the initial residual. For different values of the permeability, some more conductive fractures and some more like blocking fractures, and for different grids. So you can see that for the different considered grids and the different values of the permeability, the number of iterations that we obtain are very similar, so the behavior of the method is very robust with respect to both the grid and the value of the permeability. And also we could think about applying the multigrid method that we have proposed instead of as a standalone solver as a preconditioner of a Krylov method. So in this case, also I present some results when the multigrid is applied as a preconditioner of the flexible GM-RES method. So we can see that the number of iterations that we obtain is very similar, it's almost the same. So in both cases, it seems that the proposed method works well for solving the problem. When I said here that we use our multigrid as preconditioner, I mean that we consider one iteration of the multigrid in order to precondition the flexible GM-RES. It could be more interesting to use the method as preconditioner when we consider an heterogeneous porous media. So in this experiment, we consider that the permeability in the porous matrix is a random field. And then, in order to obtain the samples for this logarithm of the permeability, we consider this following Matern covariance function. This function depends on this set of parameters, in which first one is the field smoothness. Here we have the correlation length, and here the variance. And for the experiment, we will consider two different parameter sets of increasing complexity. So in this one, we have an heterogeneous permeability given by these parameters, and this one is much more complicated in the sense that the fluctuations in the permeability are much higher. So we have performed 50 realizations with each of the parameters, and then what we obtain is that only about 9 iterations are needed in order to solve the problem with the first parameter set, and around 13 iterations are needed for the more difficult set. So we can see that the number of iterations that we obtain here are very similar to those that we were obtaining before with the homogeneous porous medium. In the second numerical experiment, now we still consider one fracture, but now we are gonna change, and instead of constant permeability in the fracture, we will consider two different permeabilities, one in the middle part of the fracture and another one in the parts of the fracture that are close to the ends. Here, in particular, we choose a big permeability in the outside part and a small permeability in the middle, so that the fluid will flow here to the parts in the extremes and not in the middle part, as we can see in the picture, since this part will act like a barrier for the fluid flow. And in order to see the behavior of the multigrid for this case, in order to see if we have some influence of this different permeability or not, here we can see the history of the convergence for different grids. This means that we show the reduction of the residual against the number of iterations that we need in order to reduce the residual until 10 to minus 8. So we can see that just about 10 iterations are needed in order to solve the problem until the desired accuracy. So these are more or less similar iterations as the ones that we had before for the constant permeability in the fracture. Now we want to check if our method is robust with respect to the number of fractures. So we will consider first a test in which we consider 4 fractures. This is the setting of our problem. So we have the unit square, and then we have impermeable walls, and the p equal to 0 in the bottom, p equal to 1 on the top, and these 4 fractures. You can see that different permeabilities are chosen in the fractures. First we have these 3 fractures that will act as barriers because the permeability is small, and then we have this one that is a highly conductive fracture. In the table, we show again the iterations that we need from the multigrid in order to reduce the initial residual in a factor of 10 to minus 10. And again, the results that we obtain are like in the previous experiment. If we consider connected fractures, this setting in particular, again, the results that we obtain are very similar, and we see that the method seems to be robust also with respect to the number of fractures that we consider. Finally, for one of the last experiments, we consider a benchmark problem, which was proposed in this paper here, in order to test the different algorithms for this type of problems in fracture porous media. So the fracture network is the one that we see in red in the picture. This is our domain with all the boundary conditions. And then we are going to consider 2 different cases. In the first one, we consider a high permeability in the fracture network. Here we have the pressure distribution that appears after solving this problem. And then this match perfectly with the reference solution that they propose in the previously mentioned paper. And here we see the behavior of the multigrid method, in which we can see that for different grids, the behavior of the method is robust with respect to the spatial discretization parameter, and also around 13, 14 iterations, we obtain the desired convergence. In the other case, when the permeability is small, this would be the corresponding reference solution, and here we have the history of the convergence for the method. And also again, now, between 10, 11, 12 iterations, we obtain the solution with the proposed multigrid method. Finally, I want to say that well, we would like to see how well are we solving the fractures in comparison with a Darcy problem in a porous media without fractures. So what we compare here is the asymptotic convergence factor that we obtain for the examples that I just presented. And here we consider the convergence factor that we would obtain with the same multigrid method, but applied only to a Darcy flow in a porous media without any fractures. So in order to get this number, we apply a local Fourier analysis that allows to predict the convergence rate of the multigrid method. And what we obtain is a value, a convergence factor about 0.04. And we can see that this is very close to the factors that we obtain for the examples that we have presented with the fractures. So it seems that the treatment that we do in the fractures is almost optimal, because the difference, we don't have like a significant deterioration of the convergence of the method. So in order to finish, I want to talk a bit about the extension of the proposed solver for the nonlinear Darcy-Forchheimer coupling. So the idea is as follows. So we have Darcy flow in the porous media as before, but now in the fracture we have this Forchheimer law that consists of adding this quadratic term to the velocity in the fracture. Usually, it's known that Darcy flow works when we have some specific settings in which the velocity is low. But if the permeability in the fracture is much higher than the one that we have in the porous matrix, then the velocity in the fracture is much higher, and then you need to incorporate some different models in order to model the flow in the fracture. So here we have chosen like the simplest one, so this Forchheimer law, but of course it could be possible to choose a different model here. So we do the corresponding changes in the function spaces and in the bilinear forms, and then we obtain our mixed form for the variational problem. We consider the same idea for the discretization with the mixed finite element method. And then now what we obtain is an algebraic system of equations, but now it's a non-linear system. So the idea, in order to efficiently solve this non-linear system of equations, is again to use the multigrid method, but of course here we have two different possibilities. The first possibility will be to use a linearization like Newton or Picard, and then to apply the linear multigrid in order to solve on each iteration. Or the second possibility, that is the one that we consider, is to use the full approximation scheme, fast or non-linear multigrid, in which we apply the multigrid directly to the non-linear system. So this would be the two-grid algorithm for the fast scheme. So we have pre-smoothing, and the difference is that now we need to restrict the residual as well as the current approximation to the coarse grid. Then our problem in the coarse grid is a bit different due to this non-linearity of the system. And once that we solve this equation, again, we interpolate to the fine grid, we correct our approximation, and then we apply some post-smoothing. Of course, if our problem is linear, this fast scheme is completely the same as the linear multigrid. And then this is the method that we will consider together with the same components that I previously explained in order to solve this Darcy-Forchheimer coupling. So just two examples in order to see the robustness of the method. So the first one is very similar to the one that we consider in the Darcy-Darcy coupling. So we have one single fracture. Now the difference is that in the porous media we consider a much smaller permeability, 10 to minus 9 instead of 1 that was before. And then we want to see the behavior of our method for different values of the constant permeability in the fracture. So here, one example of the pressure distribution. And for a fixed value of the permeability in the fracture, we see first that the behavior of the multigrid method is robust with respect to the spatial discretization parameter. And now, with respect to the different values of the permeability and for different grids, we see that, again, the number of iterations that we obtain are almost the same that we obtain in the case of the Darcy-Darcy coupling. This is by fixing the Forchheimer coefficient to 10 and choosing different values of the permeability. Now we will do on the contrary, so we fix the value of the permeability in the fracture, and then we vary the Forchheimer coefficient. Notice that as the Forchheimer coefficient gets bigger, this implies a stronger nonlinearity, and then the problem becomes more complicated. But we can see that the number of iterations that we obtain in every case is almost the same, and we don't have any deterioration of the behavior of the method. And finally, some example with the crossing fractures for the Darcy-Forchheimer model. So we have here some example of pressure solution for this permeability in the fracture and this Forchheimer coefficient. And again, what we do is to check the behavior of the method for different permeabilities in the fracture and for different values of the Forchheimer coefficient. Again, the number of iterations are very similar. The method seems to be very robust, again, by changing the Forchheimer coefficient. And as conclusion, we have presented a monolithic mixed-dimensional multigrid method in order to solve these mixed-dimensional problems in fracture porous media. by considering Darcy-Darcy and Darcy-Forchheimer coupling. The key in order to design this multigrid method was these mixed dimensional components that we choose in the multigrid method. And then we have proved robust convergence for different cases, for the discretization parameters, for different, for different physical properties of the fractures, and for different values of the Forchheimer coefficient. Also, we see that the convergence of our method is almost the same that if we solve just the Darcy problem without fractures. And the details of this presentation can be found in these two papers that are already accepted but are not so this one is online, this is still in press. And in order to finish, I would like, well, even if we are in the first day of this YIC conference, I would like to invite you to the next one, that it will be, of course, in 2 years, but it will be celebrated in Valencia, and then we will be, Enrique, Jose, and me, will be very happy to meet you there. So thank you very much for your attention.
Now it's okay, yeah? Yeah, I would like to ask about, you have Darcy law, it's linear, yeah? Velocity pressure. Forchheimer law means that you have square term, beta.
Yeah, you have this, this absolute value, so at the end is like a quadratic term.
Okay, yeah. So I don't see, but about, okay, so.
So if you have Darcy, you only have this, and then you include this quadratic term with the parameter beta that controls.
Yeah, about 5 years ago, I, and not only I, have proved that this coefficient is equal to 0. In
the beta?
Yeah. So it begins from 3rd degree. So, but it's okay. If you are interested, I can show you.
I mean, we just found.
Yeah, I understand.
This model for these mixed dimensional methods in some paper, and we try to check the convergence of our method. But
okay.
I mean, I would be interested in in seeing your work, of course.
Yeah. Thank you.
Thank you.
Okay, next question.
Thank you for the nice presentation. I'm wondering, did you try to check the convergence rate of the whole numerical scheme? It's like more first order accuracy or second order numerically?
So you mean for the discretization?
Yes, for everything.
Yeah, what we have at the end is like a cell center finite volume scheme.
So it's more second order. Okay, that's
so
great.
It's very, at the beginning, we do these mixed dimensional finite element methods that at the end, when you use these quadrature rules, what we got is a standard cell center finite volume scheme, yeah.
Okay, and did you check it numerically with a specific numerical example?
I think when we first code the things, we checked that the reduction was right in order to see that this was correct. But then we have focus on the behavior of the solver.
And also I was wondering, but maybe this is not so easy, how difficult could it be if we further want to extend the model to consider the fracture propagation? Like we saw some hydrofracture problem, but I guess this is not so easy, but I want to hear some comments from you.
Of course, you would need to see first to have a good discretization for the crack propagation, and then of course our method is based on the idea that you choose the grid by knowing where are the fractures. So this could be difficult in order to apply this. I think we would need to think about applying something similar, but by considering maybe another different discretization that doesn't take into account the fractures like in the mesh. Yeah. But of course, it would be very interesting.
It's still under development, right?
Of course.
Okay. Thank you.
Thank you.